warahmatullahi wabarakatuh. To my panel, Dr. Muzaffar and Mr. Saiti. Good evening, Dr. and Mr. Saiti. Okay, today I would like to present my BDP1 project titled Development of Visible Light Communication System using Array LED Technique for Wireless Connectivity. Okay. A new communication technology known as visible light communication (VLC), which has the ability to quickly switch between various levels of luminous intensity, has given rise to a new communication technology. LED lamps are now being widely used for data transmission as well, thanks to this technology. It uses light pulses to transmit data, and at the same time, it can also provide illumination for the users. To resolve the problem occurs in radio frequency technology such as radio interference from other services. This form of wireless communication is recommended and is viewed as a replacement for traditional radio frequency communication. Okay, this is the problem statement. Radio frequency technology has many disadvantages and weaknesses, including distortion and high latency problems. The RF technology is also lack of security because there is no privacy, as the signal that transmits the data travels through solid surfaces and it can be interrupted momentarily. Plus, in RF communication systems, power consumption is extremely high compared to the OWC technology. Common VLC system employs single LED, and because of the lack of light and illumination, data transferred by a single LED is often restricted in space and has a shorter wavelength radius. Okay. The first objective of this project is to design and construct a visible light communication system which consists of transmitter unit and receiver unit by using array LED technique as the light source. And the second objective is to analyze the data transmission and performance of visible light communication system under various conditions such as distance between transmitter unit and receiver unit and illumination intensity. Okay, this is the scope of project. First is to focus on the construction and development of transmitter and receiver unit in software and hardware. Next, Opti system and Proto software will be used to design and analyze the electronic and optical part. Next, the result of input inserted to the transmitter and output from receiver will be compared for both hardware and software. Once it has been accomplished, it will be further compared and tested under various conditions. Array LED technique will be used as the light source in the transmitter, meanwhile the receiver will consist of demodulator and photodetector. So, for the methodology in this chapter, we will focus on information and explanations regarding the project's technique. There are three aspects that will be shown for this process. First, the project flowchart, which depicted the whole project workflow. Next, a block diagram of the entire project will be shown. And finally, the project's hardware and software will be discussed in terms of the methods and components used. Okay, this is the overall project's flowchart. Literature review was conducted based on past project research, and the knowledge collected will be implemented. The goal of the project is to construct a system prototype with the help of the Opti system software, and the prototype will then put through its paces to ensure that the hardware is working and functioning properly. Okay, this is the working process flowchart for the transmitter part, where it consists of carrier and information signal, modulator, and array LED. The signal will be transmitted to the next part, which is the receiver. In this part, it consists of photodetector, demodulator, and finally the output signal that will be received by the end user. Okay, the block diagram depicts the entire process flow of the project. First, the information signal in the pulse waveform is modulated into an electrical signal using an electrical modulator. After that, the modulated signal will be sent to a transmitter unit which consists of another modulator with array-wide LEDs. When the modulated light signal is detected, it will be delivered to the receiver unit. The demodulator will convert the optical signal back to an electrical signal once the photodetector has detected the light signal. The electrical signal is then converted to a pulse waveform by the electrical demodulator. In OptiSystem software, both optical part and electrical part will be constructed and designed. The main purpose is to simulate the optical circuit and electrical circuit and obtain the correct output at the receiver. And initially, 4 examples of electrical part will be constructed and only one optical part will be included in the OptiSystem software. The main reason is to understand the basic back-to-back analysis of the system. The input and output signal will be analyzed using oscilloscope visualizer. Okay, this is the circuit diagram that I have constructed. The example of a circuit diagram constructed in the OptiSystem software, and this is the flow of the optical system and electrical system in the OptiSystem software that will be shown in the simulation later. Next, we will proceed to the software named Proteus. It will be used to construct and design the electrical circuit. There will be 2 electrical circuits, which are transmitter circuit and receiver circuit. The main purpose is to test the functionality of data transmission via LED and receiving data via photodetector. And this is the hardware. The hardware of this project will require array LED, modulator, photodetector, demodulator, and IC chips, and many more components that will be used. The components mentioned will be used to construct the project's prototype in BDP2. Okay, this is the development of transmitter unit for the system. The transmitter of this project system includes an LED luminaire. A driver circuit is also included in the LED light, which will regulate the current flowing through the LEDs to adjust the brightness. The transmitter in this project will use visible light channel to transmit the data. This system principal function is to emit light while simultaneously transmitting data. Next is the development of receiver unit for the system. The data will be extracted from the modulated light beam using the VLC receiver in this project. The photodetector will detect the rapid flickering of the LED and convert light into an electrical signal. The microcontroller will read the input received by the photodetector and send the message to the PC. Okay, this chapter will discuss about the project, including the analysis and discussion of all the outcomes. But unfortunately for BDP1, the outcomes will be the result of all the recommended methods, but only included software method. This explanation will primarily be focused on an investigation of the electrical components and some optical components. The hardware part will be proceeded in BDP2. The simulation results show 4 examples of electrical modulation part and 1 example of optical part, where all the simulations are developed in OptiSystem software. Okay, first is the frequency modulation. So here I have sine generator for the input, which is the message signal with 30 MHz, and I have electrical frequency modulator, which is the carrier signal with the frequency of 1000 MHz. Okay, and here I put electrical amplifier with 6 dB gain to amplify the output from the demodulator. Okay, and for your information, the carrier signal must be bigger than the message signal. Okay, now I will run the simulation. So as we can see here, okay, this is the message signal, and this is the frequency modulated signal, and this is the comparison between the message signal and demodulated signal. So we can see that the message signal and the demodulated signal is similar, which means that the modulation is success. Okay, now I will show the phase modulation. So in phase modulation, I use the same parameter with the frequency modulation in the input. Just I change the electrical phase modulator and demodulator. So I will run the simulation. Okay, so this is the message signal and this is the modulated signal for the phase modulation, and this is the comparison between the message signal and the demodulated signal. So as we can see here that the message signal and the demodulated signal is also similar, just like frequency modulation, but the demodulated signal is shifted a little bit to the left. So we can say that the modulation is also a success. Next, I will move to FSK modulation, frequency shift keying modulation. So here I change the input, which I use user-defined sequence generator and NRZ pulse generator. So and here I use electrical frequency modulator and demodulator with the carrier frequency of 5000 MHz. So to obtain the output, I use the 3-hour regenerator component. So here is the pulse input, and this is the modulated signal of FSK modulation. And here is the comparison between the message signal, the input signal, and the demodulated signal. So as we can see here that the message signal and demodulated signal is also almost similar, but the demodulated signal output is shifted. So we can conclude that the modulation is also a success. Next, I will move to PSK modulation, phase shift keying modulation. So the parameter that I use in the PSK modulation is also similar to the FSK modulation, but I changed the electric by using electrical phase modulator and demodulator with the carrier signal of 5000 MHz. So I will run the simulation. So here is the input signal, and this is the modulated signal, and this is the comparison between the message signal and the demodulated signal. So we can see that the output is not similar with the message signal. The output from the demodulated signal is higher in frequency. So it can be concluded that this type of modulation is not very good, not successful. Okay, and for the final one, I will move to the OOK and RZ modulation. So in this part, I include some optical part, which is white light source with 193.1 terahertz frequency, Mach-Zehnder modulator, and FSO channel with a range of 3 meters for the distance, and I use avalanche photodiode as the photo detector to detect the white light. So I will run the simulation. So we can see here that the above signal is the transmitted signal by the white light source, and this one, the below signal, is the received signal received by the avalanche photodiode. So we can see that both the signals are similar, and we can conclude that this type of modulation is success. So, and also I can say that the transmitted signal by the white light source is similar to the signal that is received by the avalanche photo detector. So from the video that I have shown just now, I have managed to make a discussion and conclusion. So in FM, PM, and FSK, the results obtained in demodulated signal is similar to the message signal. Same goes to OOK and RZ modulation. The signal transmitted by the white light and the signal received by the photodetector are both similar. As conclusion, the most acceptable modulation types for this experiment are OOK and RZ, FM, PM, and FSK modulation. The main reason is because the received signals retrieved in the output are similar and close to the transmitted signal. PSK modulation is not acceptable because the received signal in the output is not similar as the transmitted signal. Okay, this is the project planning that I have done for BDP1 and BDP2. And Dr. Muzaffar and Mr. Saidi, if you have any questions about the project, don't hesitate to contact me through WhatsApp or email. Thank you for listening to my video, and I hope you will have a nice day.